Welcome back to real time digital signal processing course. So, we discussed about IIR filters little bit in the last class. Today we will continue with the same thing. So, as a recap, as I said, we have discussed little bit on IIR filter, how we have to design from analog domain to digital domain, what we have seen the thing. So, today we will continue on that. So, what we said was it was the structure 1, what we had taken the thing, our direct form 1. So, here we will see how biquad has to be designed. In the continuous domain, first we will see the thing and later on we will go back to the digital domain. So, we know that impulse response with biquad with poles sigma plus or minus JB, where with sigma less than 0, or I can take it as A which is less than 0, but no zeros, then the impulse response is given in the analog domain h of t is equal to c into e power minus s t cos bt plus theta. So, pure sinusoid when our A is equal to 0 and pure decay when B becomes 0. So, how we can implement in the breadboard what it is given nowadays, nobody does the breadboard design, but one can test it how it is going to be, and if you are satisfied you can go for implementation in the regular PCB. So, we consider a single pole, where is it? It is at minus 1 by RC. So, we consider 1% tolerance for our breadboard R and C values, and then C tolerance for the pole location what we assume is 2%. So, we will say that how many decimal digits corresponds to 2% tolerance, one has to look at it, and how many bits correspond to 2% tolerance, one has to look at it. So, what we want is the maximum quality factor is about what we say is 25 for implementation of analog filters using breadboard resistors and capacitors. So, if we use the switched capacitor filters, the quality factor what we said was maximum what we can achieve is approximately 40, that is for the tolerance approximately 0.2%. And then integrated circuit implementation can achieve maximum up to 80. So, breadboard you can see that it is going to be half of that of the IC's design. So, coming to the discrete part of it, so we will be representing A plus or minus JB is equal to, we put it in R into e power j theta. So, where R is given by root of A square plus B squared is the pole radius. So, assume because it is within the unit circle, we assume R is less than 1 for stability with y is equal to minus 2a. Then what happens to our quality factor Q, which is given by square root of 1 plus r squared to the power of squared minus y squared divided by 2 into 1 minus r squared, where we assume that half is less than or equal to r cube, which is less than or equal to infinity. So, what happens when the poles are real? We know that B is equal to 0, A is in between minus 1 and then 1. So, R becomes magnitude of A and y will be equal to plus or minus 2A, and what we call that is Q is becomes half, that is impulse response is C naught into A power n in that into U of n plus C1 into n A to the power of n into U of n. So, if the poles are on the unit circle, then R will be equal to 1. So, Q becomes infinity, that is we call it as oscillatory response, and imaginary poles if we have it, then A becomes 0. What happens to our R becomes, it is the magnitude of B, and y will be equal to 0, and we call Q will be equal to half into 1 plus r squared by 1 minus r squared, which is nothing but 1 by 2 into 1 plus b squared divided by 1 minus b squared. So, in the 16-bit fixed point digital signal processor, So, we say 40 bit accumulator will achieve a Q max of 40. So, you will be wondering, when we took up the architecture, we said the maximum adder length is going to be 40 bit accumulator, what we will consider. So, filter design programs often use R as a approximation of quality factor. Fine. So, how to implement IIR filter? Same approach in discrete and continuous time filter, what we will be considering it. So, the classical IIR filter designs, what is going to be considered. So, filter order of n will have n by 2 conjugate roots if n is even, or one real root and then n minus 1 divided by 2 conjugate roots if n is odd. So, response is very sensitive to perturbations in pole locations. A rule of thumb for implementing IIR filter, what is it? Decompose IIR filter into second order section, that is biquads, what we call it, and cascade these biquads from input output in order of ascending quality factors. We will see little later also how we will be working it out, what happens to our pole positions, and then how it will be affecting the cutoff frequency. We will see with little problems later. So, for each pair of conjugate symmetric poles in a biquad, conjugate 0 should be chosen as those closest in Euclidean distance to the conjugate poles. This we will see it in the next class, how it is going to be chosen. Classical IIR filter design, how it is done, differ in the shape of their magnitude responses. So, the first one, what we call it as the Butterworth filter, which is monotonically decreases in pass band and stop band will not have any ripple in that. And when we consider Chebyshev type 1, which is monotonically decreases in pass band, but has ripples in the stop band. The Butterworth, you will be seeing it, this is what we call it as monotonically decreasing, and then will not have any ripples in the pass band. So, when we come to the Chebyshev type 1, so we say I am considering the low pass filter. So, here it is, what it says is monotonically decreasing, but we will be having the ripples in this. So, when you come to Chebyshev type 2, we will have ripples in the pass band, and then it is going to be a flat response in the case of stop band. When I come to elliptical, so you will be seeing that we will be having both ripples in pass band and then stop band. So, which one do we prefer? So, that is one of the challenge one has to look at it. So, when we consider the order of the filter, it is an increasing order in this way. And when you see the pass band attenuation, whether you are going to meet a stop band attenuation, which one you want to meet it. So, we call this as my delta S, basically where it is coming, and this is my 1 plus delta p, what we had represented, this is 1 minus delta p. So, in this case, whether we are going to select Butterworth, I said the order is going to be more, whereas elliptical order is going to be very less compared to other filters, but I will be having the ripple in pass band as well as stop band. Whereas Chebyshev 1 has ripple in the stop band, whereas Chebyshev 2 have ripple in the pass band. So, compared to which frequency you want to meet. Most of the time when we use the impulse invariance method, it is better to go for the Chebyshev 2, which is going to be in between order. So, I can allow little bit of ripples in the pass band, but I want to meet the flat response in my stop band, so that no aliasing is going to happen. So, coming to order of the filter, it is, as we said, that with respect to Butterworth and then elliptic, it stands in between. So, what it says is classical IIR filters have poles and zeros, except continuous time low pass Butter filters only have poles, okay, and all classical filters have biquads with high Q factors. So, we will be seeing why we go for the biquad in a while. How we are going to do the optimization. So, we will be starting with an existing basically classical filter design, we are going to use it, and we will do IIR filter optimization packages from UT Austin, which is developed in MATLAB. Simultaneously you can optimize on the filter order. So, you will be optimizing on the magnitude response, linear phase in passband what we can achieve using IIR filter also, and then how you are going to control the peak overshoot in step response, and how we are going to take care of the quality factors one has to decide and then do the design. So, we will do little bit comparison of FIR and IIR filter in this slide. So, when we talk about the implementation complexity, so we will be comparing the same piecewise constant magnitude specification. So, for that FIR filters will have higher order, whereas IIR filters what we can achieve is with the lower. So, the factor may be 4 lower compared to higher FIR filters. Coming to minimum order design, when we want to do the thing, so we can use Pax-Maclaurin or Remez exchange algorithm. So, what is the consequence of it? To algorithm to estimate minimum order for this algorithm by Kaiser may be off by 10%. So, we have to search for minimum order is often needed in this case. So, whereas in the IIR filter design we know that if we allow deviation both in the passband and then stop band, so we can achieve elliptic design algorithm gives us the minimum order. So, whether it is stable, when we are putting a question mark, we know that FIR filter is always stable. So, we say that IIR filter may become unstable when implemented. So, we can tune design to implementation target to minimize the risk of it. So, we have to see that all the poles are inside the unit circle, so that we will get a stable filter. Coming with the linear phase, what can we achieve? So, we know that if impulse response is symmetric or antisymmetric about midpoint, then we always achieve a linear phase using FIR filters. Whereas in IIR filters we will not achieve it, but phase may be made approximately linear over passband or other band in this case. So, to conclude on the IIR filter biquad section, we will see that choice of IIR filter structure matters for both analysis and implementation. So, keep roots computed by filter design algorithms, and then polynomial deflation, that is rooting reliable in floating point. So, it is going to have polynomial inflation, that is expansion may degrade the roots of it. So, more than 20 IIR filter structures in use. So, that is direct forms and cascade of biquads are very common choices. So, why we go for the cascade in our IIR filter? So, we will discuss it in with a problem later, so that you will become convinced that why I have to go for the cascade section. In the direct form IIR structures, expand zeros and poles, it may become unstable for large order filters, usually order greater than 12th order what we call it, due to degradation in pole locations from polynomial expansion. So, most of the MATLAB, when we design our filter, we use the MATLAB FDA toolbox. So, it provides us we call it as stable filter coefficients, which we will be using it in our implementation. Coming with the further conclusion, so cascade of biquads, that is second order sections, only poles and zeros of second order sections expanded. So, what happens to this? If it is a direct form, if there is any quantization in my pole or 0, so the complete structures becomes may become unstable, whereas in the biquads if any of these poles are zeros is quantized, only it is limited to that structure and it will not affect the other order second order sections. Biquartz placed in order of ascending quality factors. So, this is going to become an optimization problem. One has to look at it and then see that how I can achieve this, and that is the way the Biquartz section will be connected. Optimal ordering of Biquartz requires, that is what it says, exhaustive search. And when filter order is fixed, there exists no solution, one solution or an infinite number of solutions. So, if you fix the order, we may not have a solution or I may have one solution. This is the way I have to connect all of them. If it is a second order, I do not have any choice, only one Biquartz section I can have it. But if it is more order is more than 2, then I can have, if it is equal to 4, I may have in that case 2 options. This can be first, that can be later, but still my poles and zeros I can alter from the sections and then see that I achieve the what I will say optimal filter structure, as well as my instability is going to be much more reduced. So, minimum order design not always most efficient in this case. So, efficiency is going to depend on the target implementation. Consider power of 2 coefficient design always, and efficient designs may require search of infinite design space. So, these are the drawbacks of IIR filter design. So, with this we will be still going ahead to design our IIR filter. So, what are the basic structures we need for designing our filters? So, as previously we have seen the thing, but still to give a feel of that how a multiplier looks. So, we will be putting an arrow, and then if I say k, then it is nothing but k into x of n. And when we say adder or accumulator is there, it can be represented with sigma or plus sign also. Then x of n and then w of n is the weight, then we will be adding both of them, x of n plus w of n. If it is a delay of 1 time, basically it can be represented by a square box. So, you can either specify it as capital D here or z minus 1. So, then we know that it is a delay element. So, x of n is the input, output will be x of n minus 1. So, coming to filter structures, just now we said that comparison we did how the order of the filter is going to be. So, here we are seeing second order Biquartz section for IIR filter. So, you will be seeing that it is a second order. For the same magnitude response, we need here FIR filter section is shown. The equation for this is y of n is k is equal to 0 to n minus 1. As an example in the table, we have taken capital N is equal to 30, then how many structures and other things what it is required we will be seeing in a while. So, whereas for the IIR filter, so you will be separating this is my W of n center point, and then second order section what we have considered here. So, W of n is given by x of n into x of n minus b 1 into W of n minus 1 minus b 2 into W of n minus 2. What happens to my y of n? Y of n is nothing but a naught into W of n minus a 1 into W of n minus 1 minus a 2 into W of n minus 2. So, since we have considered this is my feedback section and this is my feed forward section. So, this is my whole equation of second order IIR filter. So, we will be seeing how many multiplications are required. So, for the same magnitude what we said, so IIR filter needs order 2, whereas FIR filter needs 12th order. Then number of multiplications in this is going to be 12, H0 to H11. And then whereas in the IIR filter, because it is second order, so we will be seeing that number of multiplications in this is going to be 1, 2, 3, 4 and then 5. So, that is what we represent. How many additions do we need it? Whereas in this case we need 11 additions, whereas IIR needs 4 additions. You can count on the thing, because we assume the addition and subtraction as equivalent. So, you have 1 here, 2, 3 and then 4 additions. And storage locations, that is including coefficients and data. So, how many we need it, that is what one has to count. We have 12 multiplications and we have 12 what we say is coefficients for the h of n what we need it, and 12 input what we need it, and 1 output what we are going to have the thing. If current sample is not consider x of n, then we will be needing 24 locations to store both coefficient and data. Output we assume that it is going out of the memory or out of the port, so we need not have to have a storage for it. Whereas in the IIR filter, as you will be seeing that we have 5 coefficients here basically, and then the delay elements w n minus 1, n minus 2, and then what we have one of the input x of n what we needed. So, you will be seeing that 5 plus 2 7 plus 1 8 is the number of locations, that is memory what we need for this structure. As the order goes very high in FIR filter, you will be seeing that number of multiplications, addition increase, even the storage will be increasing it. So, how we are going to consider the design stages for our digital filter? So, we are going to start first, we will be specifying the performance first, and then calculate the filter coefficients, and then if everything is according to our wish, then we will go for the realizing structure what we have to select, and then see that finite word length effects analysis and solution. Once we have selected that, whether it is going to affect our input and output magnitude and then frequency responses, or it becomes an unstable filter. So, if everything is met, then we will be going for hardware and our software implementation plus testing, and then if it is not met here, we will go for the redesign of it. So, if any one of the stage here the finite word length is not met, we can go and then fine tune any one of these stages. So, if everything is feasible, then we will stop our design. So, as we said, some of the structures also matters. So, few FIR structures you will be seeing it, this one gives our linear phase. As you will be seeing that we said it is a symmetric or antisymmetric what we are going to take the thing. So, here you will be seeing that this is h of 0 that is x of n, and then x of what is the delay here you are going to get it. So, 1, 2, 3, 4, 5 and then 6. So, x of n and x of n minus 6 is combined, and then you will be multiplying with h of 0. The same way you can calculate which are the ones getting multiplied, and then you will be summing up, then you will get a linear phase. So, if you want to use the transversal, as you will be seeing that, so h of 0 to h of 6 are my impulse response, and then x of n to x of n minus 6 will be the input, and when you feed it into the thing, so you will be seeing single summation. So, you may overflow or underflow in this case. So, y of n will be the output. How much tolerance you are going to give it? As I said, we are using the 40 bit adder. So, the order of the filter in our sigma can usually we represent y of n equal to sigma k is equal to 0 to n minus 1 x of n minus k into h of k what we have it. So, this value n can be up to 255. So, which is in power of 2 if you take it 2 power 8 0 to 255. So, it becomes 256 which is equivalent to 2 power 8. So, what we say is if the our adder is 16 plus 16 bit what we are going to add or our registers are 32 bit, I can allow a overflow of 8 more bit, that is 32 plus 8. We call this as the guard bits in our accumulator. So, this we call it as a guard bit in our DSP processors to take care of 40 bit addition. So, up to 255 there may not we may not have a overflow, beyond that we may overflow in the FIR design. So, one has to take care, as we said, it is almost stable, but the order goes very high, then it may become unstable. So, what are the DSP errors we are going to encounter in our design? So, it has been listed. Main errors in DSP are, first is our ADC quantization error. So, this results from representing the input data by a limited number of bits. So, I can choose 12 bit ADC, 10 bit, 8 bit, depends on what type of ADC you want to have it. And then next is, as we have to have a coefficient to be represented in fixed point. So, I am going to have the quantization error here. So, that is what it says, represent coefficients are DSP parameters by finite number of bits. So, the coefficients AK and BK from stage 2 of filter design, for example, are normally of very high precision, but in a DSP processor they must be quantized typically to the processor word length. And then next is, once I have done the coefficient quantization error I have looked in, next is overflow error. As we are talking about addition or subtraction can give us overflow or an underflow. So, we say addition of two large numbers of the same sign which produces a result that exceeds our permissible word length. This is one more error what we have to look in. The last one is the round off error. So, what is this? This is caused when the result of a multiplication is rounded or truncated to the discrete value or permissible word length. So, when I do multiplication 16 bit into 16 bit, so I will be resulting in 32 bit, but I will not be able to represent that complete 32 bit as output. So, I will be truncating them or rounding them to 16 bit and then I will be storing. So, we have taken one example already in our fixed point multiplication and addition. So, these are the errors. So, first we will see how we are going to have ADC is going to cause as an error. So, we know that in the analog domain the values are represented in continuous way. So, my ADC input voltage, what we have it on the x axis and y axis will represent what is the value or the depends on the number of bits what I have it. So, I will be representing to one of them. So, we know that. So, from this 1 voltage to 2 voltage I will be representing with the same value and I will be changing it. So, this is the staircase what you can look at it. So, what we want, ideal converter with finite number of bits, we say that ADC characteristics is one of the thing what it required. So, what we say is it accepts analog input and generates a digital representation. So, what is the quantization step? We call it as delta. So, it is going to be minus 1 LSB bit. what it is going to be. So, if we have full scale input range is represented as this thing minus 0.5 delta to 2 power n minus 0.5 times delta. So, the total will be minus 1 what we are going to have LSB representation. So, n is the number of bits that one processor has. As an example, if we assume it is a 3-bit processor, then the full voltage scale what we can represent with this representation is minus 0.5 delta to 7.5 delta. So, this is the full scale range of our ADC. To show that how the quantizer in expanded form. So, what is this delta? So, you will be seeing that from this point to this point, this is we assume it as minus 0.5 and this side is minus 0.5. So, which will be giving me delta. So, that is what we say, that is the error what we will be encountering from our ADC quantization. So, this is represents a zoom in staircase thing. So, if we consider the PDF of quantization error, then I will be representing it as minus 1 by delta to 1 by delta, and then this is your expected value what you will be getting it here P naught E, which is what we call it as 1 by delta. So, coming with the quantization error, how we are going to calculate it. So, we have to take it as a noise. So, we will be noise variance sigma quantization noise squared what we will be calculating. So, which is nothing but expected value of our error squared. So, when we equate it, it is minus delta by 2 to delta by 2 into 1 by delta into E squared into delta E basically. So, which is minus, which is equivalent to 1 by delta into E cube by 3, and then you are substituting between minus delta by 2 to delta by 2. So, when you expand it, you will get it as delta squared by 12. So, we say that quantization noise sigma squared is given by, or power is given by delta squared by 12, and then we assume quantization noise, we that is voltage quantization noise RMS value is given as delta by square root of 12. So, that is we say RMS value of a full scale sinusoidal input is given by, if your maximum signal RMS value is represented as 2 power n by 2 divided by root 2 into delta, then we will be calculating maximum signal to noise ratio. This is my signal and then this is my noise. So, it is 20 log base what we will be calculating it. This is my signal, this is my noise. So, when we equate this, it approximately comes out as 20 log root of 6 by 2 plus 20 n log 2. So, if we approximate it, it will be 1.76 plus 6.02 n. Accurate this equation is for n is greater than 3. So, n is the effective number of bits what we are going to have it in our representation. So, it is number of bits what it says is maximum signal to noise ratio minus 1.76 by 6.02 what we will be getting the thing. So, what it says is real converters do not quite achieve this performance due to other sources of error. So, only we have taken signal to noise ratio, there may be other errors we may like electronic noise or deviations from the ideal quantization level which will cause the error more. To calculate for n is equal to 8. So, what we are going to get signal to quantization noise ratio is going to be 50 dB what I can achieve 8 bit this one. If I have n is equal to 8, then what I will be achieving is the 50 dB. If n is equal to 12, I can achieve 74 dB signal to quantization noise ratio. When it is 16 bits n, then it will be 98 dB what I can achieve, and if it goes to 20 bits what I can achieve is 122 dB. CD quality what I was telling is approximately 90 dB what we want to have it. So, we can achieve with 16 bit that quality signal to noise ratio. So, coming we will work out a problem. So, whether you have understood our dynamic range and then what should be number of bits required. So, if the dynamic range of that is DR what we call it of an analog signal to be digitized by our A to D converter is maintained at 60 dB by an automatic gain control amplifier preceding the A to D converter. So, what are the things we have to determine? One is minimum number of bits required in the A to D converter, and what will be a signal to quantization noise ratio. So, this is what we have to find out. So, just we will solve the problem. So, our dynamic range is given as 60 dB what we have to achieve. So, we have the equation 20 log or log base 10 VFSR is the full voltage what we will be considering divided by delta. So, in this case we will take it as n into delta, where n is the number of quantization intervals what I want to have it. So, when we substitute this, it is going to be 20 log 10 n. So, n is equal to 10 power substitute them 60 by 20, which is going to give me 1000. So, you know that minimum number of bits required in ADC to code n plus 1 always we take it. Quantization levels to n plus 1 different binary numbers is n should be greater than or equal to or log base to n plus 1. So, if we do that log base to 1000 plus 1. So, we say that what I need is 10 bits what I need it. So, 2 per 10 we know that it is 1024 bits what I will be representing with, that is the nearest. So, now we have to calculate signal to quantization noise ratio with number of bits selected as 10. So, if you substitute 6.02 into n plus 1.75 dB. So, which is substitute the thing, what I will be getting is signal to quantization noise ratio of 61.77 dB. So, the maximum what we can achieve, what it says is number of bits, if we substitute in this equation maximum signal to noise ratio minus 1.6 divided by 6.02. So, if you see with this equation also, you will be getting it as 9.67 bits what I needed. So, the nearest one is 10 bits. So, both this way working out and using this equation what we had it. So, both of them are giving us 10 bits. So, you can try which is going to be less than 3 bits whether they are going to match or not. Okay. So, this is what we cover in today's class. So, we will see how the filter structure is going to affect our frequency component part of it, center frequency, in the next class. Thank you.